Hey, welcome. Today, we're going to jump into something really fascinating in the world of AI defense. It's called feature squeezing, and it's this super clever, surprisingly simple way to stop artificial intelligence from being tricked by attacks that you and I would never ever see. So let's dive right in. Okay, look at this picture. You and I, we see two birds, clear as day, against a blue sky, right? But a powerful AI could be fooled into seeing something completely different. A toaster, a highway, you name it. The crazy thing is, its perception can be manipulated in ways that are totally invisible to us. And that, right there, is a massive security problem. So check this out. On the left, a normal AI sees that handwritten digit and correctly says, yep, that's a 1. But then it looks at the image on the right, and it's absolutely convinced that it's a 7. To our eyes, though, they look exactly the same. This is what's known as an adversarial example, and it's the core problem we're going to see a solution for today. So here's how we're going to break it all down. First, we'll talk about this weird blind spot that AIs have. Then, we'll see how it creates a playground for attackers. After that, we'll get to the good stuff, the squeezing solution. We'll see how it works, and finally, we'll check out the results, which are pretty darn impressive. Okay, so let's start by really understanding the problem. What exactly is this blind spot that our super smart AI systems seem to have? So, an adversarial example is basically an input that's been tweaked with almost surgical precision, all with the goal of tricking an AI. Just like we saw with that digit 1, these little changes are so incredibly subtle that we can't see them, but they're just enough to make the AI have a complete meltdown and get the answer totally wrong. Now, an attacker basically has two ways to do this. First, there's an untargeted attack, where the goal is just chaos. They just want the AI to be wrong, it doesn't matter what it sees instead. But then you have targeted attacks, which are way more sinister. That's where they want to force a specific error, like making that AI see a 7 instead of a 1. And the absolute golden rule for both? The image has to look completely normal to us. And this isn't just some fun little thought experiment for researchers. This vulnerability opens up a seriously dangerous playground for anyone who wants to exploit AI systems out in the real world. So you might be thinking, okay, so an AI gets a bird or a number wrong. Why is that such a big deal? What are the real stakes here? Well, the stakes are incredibly high. Seriously, just imagine this. In autonomous cars, AI sees a stop sign, but an attacker has put a tiny, almost invisible sticker on it. And now the car thinks it's a speed limit 60 sign. Or think about a medical AI that's supposed to detect cancer, but it looks at a dangerous mole and calls it harmless because of some subtle digital noise. We're talking about everything from security systems to facial recognition. These attacks can have literal life or death consequences. All right, so we've laid out the problem. It's a big one. But luckily, there is a really, really clever solution. So let's meet the hero of our story, feature squeezing. The key insight the researchers had was just brilliant. They figured out that the problem wasn't that the AI isn't smart enough, it's that it's paying attention to way too much detail. A digital image has a mind-boggling amount of information in it, and all that extra data, all those tiny details, give attackers a massive space to hide their malicious little changes. And that's where feature squeezing comes in. It's a defense that, get this, intentionally simplifies the data before the AI even gets a look at it. Think of it this way. If you want to find a station on the subway, you don't need a super detailed satellite map of the entire city with every tree and fire hydrant. No, you just need a simple subway map. Feature squeezing basically gives the AI the subway map instead of the satellite view, stripping away all that extra noise where an attack could be hiding. So that sounds great in theory, but how does it actually work? Let's break down the mechanics of how you squeeze the data, compare the results, and ultimately catch an attack in the act. This diagram pretty much shows the whole process. An image comes in, and it gets sent down two paths at once. First, it goes straight to the AI model, no changes. But at the exact same time, it also gets sent through one of these squeezers that simplifies it. The AI then makes a prediction on the original image and on the squeezed one. And the really critical step is comparing those two predictions. So here it is, step by step. 1, get the AI's normal prediction. 2, make the simplified, squeezed versions. 3, get predictions on those two. And 4, the moment of truth. You compare them. Now, if the image is legitimate, squeezing it shouldn't really change the AI's mind much. But, and this is the key, if it's an adversarial image, squeezing it often destroys the attack. The AI's prediction will suddenly swing wildly. And that huge difference? That's our alarm bell. That's the red flag. So one way to squeeze an image is to reduce its color depth. A normal digital image can have like over 16 million colors. But do you really need all of them to tell what's in a picture? This method just dials that number way down. As you can see, the picture still looks totally fine to us. But that process squeezed out all those super subtle color details where an attacker could have hidden their trap. Another method is called spatial smoothing, and honestly, it's basically just a very gentle blur. What it does is it averages out the values of pixels that are next to each other. So look at the manipulated image on the left with all that sneaky noise. After you smooth it, like on the right, all those tiny microscopic pixel changes that were fooling the AI, they just get blended away. It's like you're cleaning the image and neutralizing the attack. Okay, so the idea is simple, it's elegant. But does it actually work? Is it effective? Let's get to the good part and see how this thing actually performs against real attacks. And the results are just fantastic. When they tested this framework against a whole bunch of different attack methods, feature squeezing got incredibly high detection rates. On the handwritten digit dataset, it caught 98% of attacks. And on ImageNet, which is a much harder dataset with complex photos, it still nailed a really strong 85% of them. Let's just pause on that for a second. 98%? For a problem this tricky and this dangerous, being able to catch almost every single attack with such a simple idea, that is a huge win. And here's the other great part, it's reliable. The false positive rate, that's the chance it accidentally flags a perfectly normal image as an attack, is only about 5%. So the system isn't just crying wolf all the time. It's genuinely good at telling the difference between real and fake. And this is absolutely crucial, because feature squeezing only messes with the input and doesn't touch the AI model itself. You can just bolt it onto any existing system. You don't have to do any expensive, time-consuming retraining. It's kind of like adding a really smart security guard at the front door of your building. You make the whole place safer without having to renovate a single room inside. And all of this leaves us with a really fascinating final thought. You know, we spend so much time and energy trying to make our AIs more complex, more powerful, able to see every last detail. But what if the key to making them safer, and maybe even smarter, is to teach them how to ignore all that noise and just see the world a little more simply? Could their best defense actually be seeing less? Thanks for watching.